Welcome to the physics laboratories corridor, where many interesting experiments happen. But today I will show you first the water lab and then the DLS lab. But of course, the water lab is at the very, very end of the corridor. So follow me. And welcome to the water lab, where we make experiments with super cool water and high pressure amorphous ices, or as some people call them, cosmic ice. So if you follow me, I will show you the piece of equipment that we use for making these amorphous ices. And this equipment that we use is basically because we need to use very high pressures to generate these specific ices. As I said before, we cannot use something very heavy or a very heavy animal like the elephant that I showed. So we have to use a very big testing materials press. So if you can see here, it's a really big piece of equipment. So from this you might think that our samples are really, really big, or at least in the size of this machine. But in reality, our samples tend to be really, really small. This is one of the sizes, roughly, but they can be even smaller than this. So can you imagine having such a tiny sample in such a big equipment? Well, that's what it takes to make amorphous ice. Not to mention that everything needs to be really cold under liquid nitrogen conditions. That's why you see all that frost. Now, of course, when we're pouring liquid nitrogen and so on, it can be very easy to, well, basically harm yourself because you can get burns. And that's why we always use this equipment, at least the gloves. You can even use an apron to cover yourself. However, our samples are very, very small, as I told you, so these gloves that we have might become a bit inconvenient. But yet we cannot touch our samples. Imagine what happens if you touch the ice. Well, of course it melts and all the work we've done will just be ruined. So we tend to use very fine materials here. We use, if you come all the way here, you will see we use, for example, these tiny, tiny tweezers. And these are actually Teflon, because when you use directly something like this will get very cold and then you get burned. So you usually need to have Teflon. So we tend to have a table prepared kind of like in a surgery, basically, because we need to have all of our material ready to be cooled and to be used so that we can handle our samples without destroying them. And this is here where we store our samples. So if you see, we have isolation, and then these walls are also isolated. And we have to fill this with liquid nitrogen. And it's stored in this kind of cylinders. But the good thing is that once it's in this kind of shipper, imagine, we have sent our samples all the way to Korea and they still survive, all nice and cold, without any transformation, without any new crystallization forming. So yes, for sure, we're doing cool experiments in more senses than one. But also, we would not be able to do any of it if there wasn't the technology for it.
And now follow me to see the DLS lab. So now we are about to enter the DLS lab. DLS is the dynamic light scattering. This is the technique that allows us to measure nanoparticles or proteins in different solutions and the dynamics of these particles, and then infer something about the properties of the solutions. Before we go in, I'd like to say a few words about the mechanism of this technique. So imagine you have a particle, and then you shoot light at this particle, and the light is scattered off the particle. And then imagine you have two particles, and both of them scatter light. And then these light waves interfere with each other, and if they are still, you get a very stable interference pattern. But if they move relative to each other, you get a variation of the intensity. So we measure the intensity, and by analyzing it, we can construct what is called a correlation function. And this is done in a way that we compare the intensity at single time point with an intensity at other different time points. And by this, we construct this correlation function. And from the shape of this correlation function, we can understand how the samples behave, whether they are small particles or large particles, fast or slow, and how they like their environment. So let's come and see.
Since we are entering the laser lab, safety first. So I put on my laser protection goggles and come in. Hello, Sarita. Okay, now we come to the Dls setup. Here it is. Here we have the laser coming out, and the laser beam hits the sample over here and gets scattered, and the signal is collected by the detector and then analyzed by the correlator. We can also measure the signal at many different angles, which will allow us to obtain even more information about our sample. So my first sample is a solution of silicon nanoparticles of 100 nanometers in diameter in water. And I put the capillary with the solution into a bath connected to an external thermostat, which allows one to control the sample temperature between 260 and 300 Kelvin. And I need to close the Decalin bath and also close the lid so that no laser beam comes out. Here we go. And now I go to the computer to start their measurement. It is going to take a little bit of time until the laser goes to its maximum intensity. And after a few seconds, we'll start getting the signal and already the correlation function. For 100 nanometer nanoparticles that we measure, we obtain the correlation function, which can be fitted very nicely with a single exponent decay and shows a decay time in the order of sub-milliseconds, which agrees pretty well with the estimations for this size of nanoparticles in water at room temperature. So now we go on to the next sample, which will be 20 nanometers nanoparticles in water. And we do the measurements again and see that the correlation function decays faster than the one we measured before, which makes sense because the smaller particles move faster whilst the larger particles move slower. And now let's see the third sample. As this third sample, we are going to have a solution of fullerenes with the dimensions in the order of 1 nanometer. So very much comparable with the dimensions of water molecules. Now, unlike silicon nanoparticles, this fullerene solution exhibits a two-component correlation function. These two components can be very nicely resolved as they decay on different timescales. You see that the fast component decays on a microsecond to sub-millisecond timescale, while the decay of the slow component is nearly 100 times slower. So the fast component can be assigned to the dynamics of mainly single molecules, and the slow component can be assigned to the movement of clusters of fullerene molecules. A similar shape of the correlation function revealing the aggregation of solutes is often observed for highly concentrated protein solutions, where the proteins do not have enough space to move around freely, so they get to stick together and move around in clusters.